Welcome to Pre-Calculus. Today we will investigate finding partial sums of geometric series. We'll take a look at four examples. The first is a series given in a sequence, and then we'll take a look at two series that are given in sigma notation, and then finalize with a word problem. Our first example here gives us a sequence 2, 6, 18, 54, and 162. And what we want to do is evaluate the related series of this sequence. So remember, the difference between a sequence, which is just a list of numbers, and a series really involves an operation. A series is really a sum. So if I were to write the associated series to the sequence, it's 2 plus 6 plus 18 plus 54 plus 162. So like we do with arithmetic series, with this geometric series, I can just add up those values. That would be really what I would do to evaluate the series. So we can do so if it's a simple short series like this by just pairing them up. 2 plus 6 is 8. 18 plus 54 is going to give us 72. And 162 is a spare value. So 8 and 72 are 80. So 162 plus 80 is going to give us 242. And that's really, with the simplest of geometric series like this one, you can just add up the values. Let's take a look at an example where the series is given in sigma notation. So here I've got sigma notation from n equals 1 to 8 of the series that's governed by the explicit geometric formula 6 to the power of n minus 1. So just to think about what's this sigma notation really describing, it's saying that I've got from 1 to 8 terms. So there's 1, 2, 3, 4, 5, 6, 7, 8 terms in the series. And if I were to just calculate some of these values, I'd start by taking the explicit rule there, 6 to the power, instead of n, I'll write 1 minus 1. So that's 6 to the power of 0 or 1. So my first term is 1 plus 6 to the power of 2 minus 1, which is going to be just 6. And then 6 to the power of 3 minus 1, which is going to be 36, and so forth. I would really just keep multiplying by 6. So I'll just put dot, 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 and that would go up to 6 to the power of 8 minus 1, which would be 6 to the 7th power. And just to see what that would look like, 6 to the power of 7 is a really large number. It's 279,936. So there would be some intervening terms there, but that gives us the idea of what that looks like. So it's not really convenient to list them out. The 8 terms is not too many, but even on the 8th term here, it's very large. So what we're after is a formula that I can use to just directly calculate what would the sum be if I were to add up those 8 terms in the series. So for a geometric series, the sum that we've got, if it's finite, so we do have to note that there's a difference between having 8 terms versus infinite terms. And you'll know it's finite if this number at the top of the sigma notation is actually a number instead of the infinity symbol. So our sum formula is going to be S sub n is equal to this fraction. So it's the first term, a sub 1, times this difference, 1 minus r, that's the common ratio, to the power of n, over 1 minus r. So that gives us a feeling about how we can calculate it. All we need to do is fill in a sub 1, r, which is the common ratio, and then our n value, in this case, is 8. So we'll calculate here. We're calculating the first 8 term sum. My first term that I calculated here was 1 times 1 minus the common ratio is 6. I'm multiplying by 6 each time to the power of 8 divided by 1 minus 6. So again, to calculate this sum, I just need to take this to a graphing calculator, a scientific calculator, plug in, evaluate. So we'll head over to Desmos. And we'll type in that expression that we wrote. So it was a fraction, and we'll put that 1, it doesn't really change the value, 1 minus 6 to the power of 8, all over 1 minus 6. So the way that's set up, it's giving us a sum of 335,923. So again, it's pretty quick to calculate using that formula, not so if I were just going to list the values out. So I'll just record here, this is equivalent to 335,923. So having a formula like that is really time saving. It also cuts down the potential for error. Let's take a look at a second example involving sigma notation. So here I've got a geometric series described from index values of 1 to 9. And my explicit formula has as its initial term -2. That's my a sub 1 times the common ratio of -1/3 to the power of n minus 1. So again, just to think about what does this series look like, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. And I find that based on the indices from 1 to 9, there's 9 terms. And just to see really what am I adding up, it's -2, if I use the explicit formula, -2 times -1/3 to the power of, in this case, 1 minus 1. So that's power of 0. This is going to become 1. My first term is -2. Let's see how this series looks like just by kind of looking at the first few terms. -2 times -1/3 to the power of 2 minus 1. So that's really -2 times -1/3. That's 2/3. So I'm seeing because this common ratio is negative, the series is going to oscillate back and forth between negative and positive. Just to illustrate that, let's find the next term, -2 times -1/3 to the power of 3 minus 1. So -1/3 squared is going to become +1/9. That's going to be -2 over 9. And so I do see that oscillation. The first term's negative, second's positive. I wrote the third term in the fourth term place. Third term would be negative. And we should see that switching, that oscillation back and forth all the way through the series. Just to see what my ninth term is, -2 times -1/3 to the power of 9 minus 1. So that we can calculate, it's going to be -2 times -1/3 to the power, in this case, of 8. And this doesn't want to calculate that. So let's just take it to Desmos real quick. We'll put in -2 times -1/3 to the power of 8. And we want that as a fraction. So that's -2 over 6,561. So one thing I notice as well, not only does the series oscillate, it also, the absolute value of these expressions gets smaller and smaller. -2 over 6561, very small number, very close to 0. Well, let's find the sum. So with this example where it's a lot of fractions and oscillation back and forth, it's an additional challenge. So having a sum formula is very useful here. So again, this is a finite geometric series. It's headed to the 9th value instead of the infinite value. And we're going to plug in again just to have that formula handy. It's the first term times 1 minus the common ratio to the power of n all over 1 minus the common ratio. So we'll set that up for this specific question. This is S sub 9, since we're adding up the first 9 terms. A sub 1 we found was -2. Again, you can see that in the way the explicit formula is written. Times 1 minus the common ratio is going to be -1/3. So I'm going to put that -1/3 to the power of n. My n value is 9. So notice I'm using ample parentheses here, all over 1 minus -1/3. So once I've got that recorded, just like we did with the previous example, I want to take it, input it into the calculator, and just get a value. So I'll write that one down. And let's jump over to Desmos. So we started with a fraction. My first term's -2. 1 minus common ratio of -1/3. And we're raising that to the power of 9. And that's all over 1 minus, again, the common ratio, -1/3. And I'm getting here a decimal value. I really like that as a fraction. So Desmos is real convenient. I just click that button to the left where it shows the ratio setup. This is -9,842 over 6,561. So we'll just head back to our note screen to finalize that answer. So the sum, and again, it's really challenging with this one because of the way that it goes back and forth from positive and negative, but the formula really is helpful here. So it's -9,842 over 6,561. So we've looked at 2 examples of these sigma notations, one where it was a positive common ratio, here a negative fractional common ratio. Let's take a look at a final example that involves a word problem. So here we've got this situation at a new job. An employee's starting salary is $26,750. He receives a 1.6% annual raise. We want to find his total earnings at the end of 5 years. So I do want to include a sigma notation expression to represent this situation. So we're calculating from the first year, so n equals 1, to the 5th year. So that'll tell me my index. And then I want to write an explicit finite geometric formula that I can use in my sigma notation. So my explicit formula for this geometric series is going to be, again, just to remind how we would write that, that is a sub n equals the first term, a sub 1, times the common ratio to the power of n minus 1. So thinking about the situation, we know that the first term is going to be the starting salary, $26,750. And we're going to multiply that times the common ratio. So we got to build that. The employee is getting a 1.6% annual raise. So it's going to be the starting salary. We'll represent that by the 1 plus the decimal value 0.016. So this is going to be a decimal ratio. It's 1.016. to the power of n minus 1. So that's my explicit formula here. We'll put that with our sigma notation, 26,750 times 1.016 to the power of n minus 1. So I've represented that using sigma notation. What I want to do now is evaluate that partial sum. I want to evaluate from n equals 1 to 5. So the formula to evaluate there is, again, S sub n equals a sub 1 times 1 minus the common ratio to the power of n over 1 minus r. So for us, the way we're going to set this up, it's going to be S sub 5. We're interested in the first 5 years added up. The initial salary, 26,750. 1 minus the common ratio was 1.016 to the power of 5, all over 1 minus 1.016. So just like we've done with those previous 2 examples, I want to record this and then we'll calculate it on Desmos. We'll head over there right now. And really similarly to the way we input these others, I'll start with a fraction. The first term in the series is that initial salary, 1 minus 1.016 to the power of 5, all over 1 minus 1.016. And over 5 years, it looks like if we were to add up this person's salaries, including the 1.6% pay raises, should be a total of $138,099.03. We'll head back to our note screen to finalize that value. So again, that has the value of about $138,099.03. Well, thank you for joining for these investigations of evaluating finite geometric series. We've looked at a total of 4 examples, one that was just a list of values, 2 that were in sigma notation, and then a 4th example that was a word problem. Again, thanks for joining. See you soon.